Thank you very much. Thanks for being here, and let's see what I can do. So well, there will be, as you will see, a sort of introductory part that, well, for many of you might be a repetition, but it may at the same time be a little bit entertaining for a Monday morning. So this is what is included in this long forward that I have here presented. So it's all about, again, limits and limitations or extensions of Poincaré. This is what Carroll is about, and maybe the first bit that I should remind you is a classical non-relativistic limit, which is the one that is better known, which is actually leading from the Poincaré group to the Galilean group. And at the same time, this is at the level of the symmetries of the space-time. At the same time, the space-time itself, which used to be Minkowski in the relativistic Lorentzian case, will rather become what is called the Newton-Cartan, which is basically time in this simple case and the Euclidean three-dimensional space. Now, there is an exotic limit, which is the one that is about this meeting, which is what we should call the ultralocal limit. This is obtained when V, the ratio V over C, rather goes to infinity. And in this case, the Poincaré group becomes the Carroll group, and the Minkowski space-time becomes a Carrollian manifold that I will discuss a little bit better. Now, besides these limits, in the sense of, taking C goes to 0 or to infinity, there is also another sort of frame where the Poincaré group appears, which is rather an extension, and this is about the asymptotic symmetries of asymptotically flat spacetimes that were actually shown in the early 60s to be not Poincaré, but rather BMS group. This is what is here, BMS4. This is for four-dimensional space, and of course you can go beyond 4 dimensions, but in this lecture I will mostly be discussing 4D. Sometimes there will be generic D, but this will be very marginal somehow. So, ultralocal limit. So this is pictorially. I go back to Minkowski, the usual space-time diagram, where I keep C, of course, finite, and I keep it separate from T, so that the slope of the light cone is rather at 1 over C, and therefore when C goes to 0, formally this means that the light cone shrinks, and therefore by law, motion is forbidden. Now, this is, of course, you can allow tachyons, as we can allow tachyons, of course, in Poincaré, and discuss them. Of course, this is, again, this motion is forbidden is from the point of view of a point-like particle. You could, of course, go beyond point-like particles and study brains and then discuss other issues. This is not what I will discuss, but we have to keep in mind that whenever one states something, this is within a certain framework, and we should keep this framework in mind. Now, so the geometry of the space-time that appears, actually, going back to formula, to give formulas to the previous diagram, well, I consider again the Minkowski metric, but now since C squared has gone to 0, this is absent. So the metric actually, which appears here, is degenerate. It has a one-dimensional kernel, and this is represented by the zero norm vector, which is called the field of observers of the metric. Right? So this is the simplest case, which is Minkowski going to the simplest Carrollian spacetime. Now, why Carrollian? Yes. Okay, that's absolutely true. It has been possible to put particles together and then somehow overcome this absence of motion. So this is why I say this is a very specific framework, and you should, of course, whenever you go to explore other things, you may have other surprises. So I leave that free, of course, to the various contributions that have been made in this direction. Thank you, Stefan. Now, why Carrollian? So this is, of course, the standard reason that goes back to Lévy-Leblanc, and he was, of course, referring to the novel by Lewis Carroll, Through the Looking Glass, together with Alice in Wonderland. And here is a discussion between Alice and the Red Queen, and Alice explains that in her country, whenever she wants to go to a place, I mean, if she runs fast enough, she will eventually reach the place. But the Red Queen says, no, here is different. Here is different. You will see it takes all the running you can do to keep at the same place. And this is the reason why actually Lévy-Leblanc had this idea of naming this what he was considering as a frivolous, actually, observation under Carroll. Now let's make it a little bit less frivolous. And now I'm here referring to the original revival works that were essentially between Tours, Cambridge, and Marseille. And this is here, I start with the invariance under Laurent's group, and I'll show how the Carroll group appears. So Poincaré group, rather, for ordinary Minkowski space-time. These are the isometries. You have 4 translations and 6-point transformation, and these are the rotation and the boosts. Now, the boosts are triggered by a parameter, which is the velocity, the relative velocity of 2 frames. Now, this, of course, should ultimately go to 0 because of the law that you shouldn't go faster than light, and light goes at 0 velocity. Therefore, I expand VI in powers of C, and I keep actually the first one, which is the one that will remain. There is a C square there. And BI has dimension of inverse of velocity. And of course, as long as C is finite, these BIs are bounded by 1 over C. But the moment C goes to 0, these become infinite. And this is exactly the sentence of the Red Queen, that all the running you can do. So you can go even to B goes to infinity. You won't fix the problem. You'll stay at the same place. Now, if you perform this transformation inside our beloved Lorentz transformations, which are here in light gray so that you don't spend time in details, you find that the time should transform in this way, whereas the space remains invariant. So this is somehow the dual picture of the standard picture of Galilean situation. Here, the time can change as a function of time and space, whereas the space can not change. I mean, if you can perform rotations, this is in the other part, which is, of course, remaining as it was. So from the more mathematical perspective, this is to saying that, the isometry group is an Inanu-Wigner contraction of Poincaré, and this is how Carroll group appears into the game as a semi-direct product of translations and rotations plus Carroll boosts rather than Lorentz boosts. Yes?
You say that this is one of the,
Yes, yes, this is the one that I agree. You can, I mean, there is a whole web of possible contractions that you can make. You can include that in Bergman spaces, etc. You can do things which are more general. This is the most modest situation that I have. Other comments? You are free, and it would be nice if you interrupt me. Yes. Yes.
These are not classified. No.
So there is an apparent disagreement on which I'm just a witness. But it's fine. No, but say more. I mean, it's not. I mean, I like this. It's better. I don't mind. I mean, I have a limited amount of time. You can even come on the blackboard with the chalk. I don't mind. Yes. Strict Poincaré.
I agree, of course. Well, that is
All right, so let's keep that, right? No, but it's all right. Yes. Yes. It's in Duval-Gibbons' favor, yes. Yes, Levy-Leblond didn't write everything he had in mind. No. It's a different this, but I found this more relevant. This is, okay, for those who do not know, this is a citation that I have borrowed from the paper of Gibbons, Duval, and Horvathi maybe, and they borrowed from Carroll. No, but you know, this is the entertaining side of it. Okay, good. So let's move. Now, example of of manifolds of Carrollian spacetimes that appear. For the moment, these were theoretical. Now, these are somehow concrete realizations, and this is the case of light cones. So you go back to Minkowski. You consider outgoing light rays in one direction. Outgoing means going from negative x to positive x. They obey this equation. Right, this is Ct minus x is constant, u is the famous retarded time. And these, of course, define a null hypersurface because this is a null hypersurface. Now, the induced metric on this three-dimensional null hypersurface, well, you obtain by considering the Minkowski metric and plugging inside the condition that you have to define, the defining condition of your surface. And then what you find is dy z squared plus dz squared. This is, of course, this looks like a two-dimensional Euclidean, but it is not two-dimensional Euclidean. It's three-dimensional Carrollian, where there is, of course, a direction which is null. So these are mostly the situations that we are facing. So the situations where null hypersurfaces appear. So there are, of course, black hole horizons, which I set here in gray because I will not discuss black hole horizons, but this is an example where typical null hypersurfaces. And the other one, which is the asymptotic null infinity of gravitational fields, which are produced by localized mass distribution. This is rather the case that I will be discussing in the following. So just to remind you how this looks like and compare at the same time with anti-de Sitter. Yes, please. Well, because you know that the hypersurface is three-dimensional and it is recubed to the metric which has only two non-zero eigenvalues. So this is how you conclude that there is a third eigenvalue which is zero. Right? So this is there is nothing mysterious behind that. You know that the null hypersurface that you are dealing with is three-dimensional in the example that I have considered, and its metric has only two non-zero eigenvalues. That's what you conclude, that there is a vanishing eigenvalue, and therefore this is a Carrollian manifold, though at least according to the simple definition that I had given. Right? Other questions? So here is just a picture of that. You know, you start the one which is here on my left side is anti-de Sitter. Well, I mean anything that is asymptotically anti-de Sitter, and you recognize this vertical hypersurface, which is a time-like hypersurface, the conformal boundary of anti-de Sitter. And then when the cosmological constant goes to zero, so usually the cosmological constant is parameterized in terms of an inverse radius, k, right? K goes to zero, therefore, since the radius goes to infinity, if you somehow want to see flat from anti-de Sitter, what you find is rather this famous corner of Minkowski, where you have Scri plus and Scri minus, and these define both a null hypersurface, which is a null conformal hypersurface. This is more than what I said before. There is a further conformal structure which is defined on this. And this is a Carrollian geometry, and this conformal structure actually is specific and gives a specific isometry group to this boundary, which is the conformal Carroll group in n-1 dimensions, which is actually under these conditions identified with the asymptotic symmetries of the asymptotically flat spacetime. So this is how null hypersurface and Carrollian geometry appears in the case that we are here discussing. Yes, please. Special infinity. You mean how? Oh, wait a minute. You are asking me how I could see this thing bending into that. Well, I don't know if I should see it this way. I would, but this maybe other people can comment. I should rather see this vertical, the whole thing going to I0, the I plus remaining, and then the I plus and minus appearing as I don't know how. I wouldn't say, maybe you have better comment. No, but wait a minute. In these diagrams, the question is more subtle. I think, as far as understood, is in these diagrams how you would from these diagrams take the limit and find the other one. What are the pieces? So it's clear that you need to go in a certain coordinate system and make the analysis in a way that this has been discussed. I would say recently again through considering the I0 blowing up around and see what's going on. So I cannot at this stage answer how exactly the species will go together. This is, of course, this is an approach, but you may have other discussions.
Exactly. You have to trick the non-radiative region.
All right, so thanks for these comments. Unfortunately, I was not able to answer very precisely, but I don't think there is at this stage a better answer. Now, let me move to, the approaches around the Carroll in general, well, are two theme-oriented. There is, of course, a geometry on one side, and people have studied Carrollian manifolds and connections that you can add, and then torsion, because these are a sequence of features that you can describe, and applications. Now you have hardcore applications, what I consider as hardcore applications, like studying dynamics, well, conformal Carrollian field theories and representation theory of BMS, bulk from boundary reconstruction, and finally, possibly the possible applications to flat space holography. And there are other things that are also nice to discuss, thermodynamics, well, more exotic excitations, and even sometimes cosmological applications. But I wouldn't put that at the center of the analysis. All right, so therefore, to conclude this long introduction, what I will here present are basically some geometric features regarding connections and torsion, dynamics and equations, because I will need that in the next step, which is a modest step towards flat space holography. So let's start with the Carrollian geometry, and let me start with some basic things. So the basic ingredient, so now I abandon the standard Minkowski paradigm that I have used, going to some more general situation. And so you need a space, D plus one dimensional space, which is equipped with a degenerate metric. So this is why this bit has been written explicitly, 0 times mu square. And there I have delta A, B, theta A, theta B. So I will be working in Cartan's formalism. So in this, you have mu, which would be the time direction of the coframe, and then theta A and theta B, which are the space directions of the coframe. These are forms based on some coordinate system that you may have chosen. And there is a kernel for this metric, which is called the field of observer. I call it nu. This is not nu, this is epsilon. And so you have spatial tangent vectors, EA. These are dual to the forms that I have considered. And there is a clock form, which is the dual to epsilon to the field of observers. Now, this construction, the way that it is set here, is invariant under local transformation. There is local, like in ordinary Lorentzian space, simply that here is not the Poincaré or the Lorentz, but it is the Carroll, so you still have the rotations, and I have given here explicitly the transformation rules that this applies. So this W, these are functions of x and t, of course, these are functions, this is local gauge transformation. These are antisymmetric because those generate the rotations. And then you have d-Carroll boosts, which are a little bit peculiar if you compare them to Lorentz boosts, just because there is this degenerate structure, and this is the way that this appears. So in particular, the field of observers is invariant, and the spatial directions of the coframe are also invariant. Right? So now, well, I have advocated, and we have, I mean, in this, I will advocate in this course, and this is the philosophy that we have been using, to separate time and space. So, well, commonly, what people do is that they consider a general covariant framework. So they have a degenerate metric, which is written in this form. So in this case, mu are coordinate indices, and they run from 0 to d. They take d plus 1 values, and the field of the kernel, the field of observer has also n plus 1 coordinates. And from that point, well, it is standard to perform a transverse decomposition. So you have the time and the space, you have a transverse decomposition, and from this transverse decomposition, you reconstruct well, an inverse metric, but it is a pseudo-inverse metric because it is really inverse in the transverse direction, and of course it's fake inverse in the time direction. I find personally this rather heavy, and in a sense not such a good application, because here there is a fiber bundle structure. There is a privileged direction, which is the fiber direction. It is very natural to single it out. It doesn't change anything in the results, but the presentation, in my opinion, gains in simplicity. So basically, what that means is that we consider a reduction with respect to the rotation group at the level of the coframe or at the level of the frame. This is what it means, right? It means that we are considering, in a sense, since time, you cannot raise and lower the index, you don't put any index. You consider these as scalars. And then you have the spatial components, which carry only space indices. And there you can move the indices up and down with the metric, which is a transverse metric. Now, here the transverse metric is just delta AB because I have been using the Cartan frame. But this is not necessary. There is an alternative, for example, parametrization, which is a sort of hybrid. Right? This is also one that you can use, or that we have been using. Well, you write the clock form as, you expand it in time, direction, and space. This is very standard. This has nothing special. The degenerate metric will be itself parameterized in this way, where these forms are also expanded in time and space in this very specific way of doing things, because this makes it easier. I will not use that. This is just to illustrate how you could do if you don't want to use Cartan. Field of observer has also legs in time and space with this specific parameterization, right? And then here, the difference with respect to the previous Cartan situation is that you reduce, not with the rotation group, because you are no longer interested in what happens in the tangent space, but with respect to what we call the Carrollian diffeomorphisms. So these are diffeomorphisms that mimic the Carrollian boosts, right? The time is mixed with time and space, whereas the space is just mixed with space itself. And with this parameterization, you have nice scalar densities. You have connection, like Ehresmann connection with transform with the shift, and the rest transforms nicely as a tensor should transform. I don't want to spend too much time on this framework. We just, in the end, raise and lower the indices with A's. So this is a parenthesis. I will not be using this, but keep in mind that this is an alternative to the other one that I will now discuss. Now I will discuss affine connection, right? So, but are there any questions regarding the previous? Yes. Yes. No, I don't impose any restriction on it. Well, 0 might be degenerate case. In that case, the vector field blows up, yeah. Well, I haven't. Yes, I mean, there is, I have, in a sense, even though I don't state it, I consider that it is finite. As Adrien was saying, the volume form will blow up. Okay, it's a peculiar limit. But, you know, C goes to 0 was a peculiar limit. So I don't disagree with the extensions, but this is my answer. Good, so let me therefore move. In a few words, say a few words about the affine connections that you can equip this. Now, as we said, to summarize, we have something, we have a manifold, it is equipped with a degenerate metric, it has a field of observers, I have added a clock form. Now, the question is, you want to define a connection, covariant derivative, so this is the next step, right? And therefore, you have to add this. So now, usually, but this again, this is not a rule, you can deal with what are called the strong Carroll manifolds, where you impose that this connection is compatible with the metric and with the field of observers. So these two quantities are parallelly transported. This is the meaning. Now, how do we deal with all that? Well, well, first of all, you have the frame and the coframe. So first of all, you can write down the exterior derivatives of these two things, and this capture all information that usually you have in the frame and the coframe. And the metric here plays a very, you know, the metric as delta AB plays an aside role. It doesn't contain much information. Now, you impose the field of observers compatibility. This means that you impose that the field of observers, epsilon, is parallelly transported along space, along time, and along space. So from these two, you don't learn any bit. It's 0, it's empty. All information about the connection comes from the other parallel transport pieces. So this is the nabla of EA, so the space transported along time, and the space transported along space, right? And this is the most general thing that you can write down. Now, once you have written down this thing, well, you can move and compute the torsion to form. Because the torsion to form, remember, will be based on the exterior derivative of the frame and on the connection. This is a mixture of these two things. Now, when you do this computation, you have the time direction and the space direction, and this is the result that you obtain. This is a two-line computation. It's very simple and very easy. As I said, it mixes the information about the frame and the coframe and the information about the connection. Now, at this stage, you want to impose, for example, metric compatibility. At metric compatibility, you do that again by taking the metric, the delta AB, computing covariant derivatives, setting them to 0, and then you extract information, and this information appears as symmetric part of gamma AB. Remember, gamma AB appears in the connection, should vanish, and the symmetric part of the gamma with one index down, the symmetric part with the two extreme values should also vanish. Now, first observation from this is the following. This symmetric part is vanishing. Now, if you go back to the torsion, you demand that this symmetric part is vanishing. But the symmetric part of CAB is not something that you control. You have given a frame, it has a CAB. So it may or may not be 0. Therefore, you don't have a control over the torsion. This part is generically non-vanishing. You generically have a torsion. So this is a very simple computation that immediately tells you that under the conditions that we have assumed, there will be a torsion, at least on this side. Of course, you may, at best, kill the other term. This is what is usually done. You can kill this other term. And in this case, you build completely the value of the gamma ABC. So those quantities which appear there are completely determined by this condition, absence of this piece of the torsion and metric compatibility. Now, you can go further and minimize, in quotation mark, the torsion, so kill another bit of its part. So this fixes for you the anti-symmetric part of the gamma with the two indices in terms of the data that you had from the frame. And you can also, and this is what we have been doing, it is not necessary, but it is also nice at the same time, kill these two other pieces of information, beta, alpha, beta, and delta. Let me go back just a minute to show you where these appear. These appear here and there. So by doing so, you switch on this piece of the torsion. If you don't want this piece of the torsion, you can simply say that the delta should be equal to phi and the beta should be equal to the pi. This is another option. But I like better the first one, even though there is no contradiction. You can go ahead and do many things with both. I like better the other because with the other, I respect the time and space splitting that I had from the very beginning. So in other words, I can consider really a vector in the sense of reduction with respect to the rotation group. And if I act with the covariant derivative on this vector, it will still be a vector. In the sense, it will be still reduced with respect to the rotation group, right? This is an option. But if you accept these choices, this is the final expression that you will have for the torsion. It is non-zero, or it could be possibly zero if you impose further conditions, but not generically. But this is for the torsion so far. I will not discuss the curvature because this is not supposed to be a course on differential geometry, but you can at the same time take the expression for the Riemann to form and compute the Riemann to form with the data you have, and then see what are the bits, split them in time and space, and use them, right? Now, the reason why we are considering this, we are making this choice, is because with this choice, the coframe determines completely the connection. So any other sort of ambiguity which appear is killed by our choice. And this is nice if you want to reach this sort of setups, of connections, through a limit from a Levi-Civita connection of a Riemannian manifold. Because in that case, you don't have any further ambiguity to start with, and you don't have others in the end. But this is, again, there are alternatives. You can keep all these things different from zero, but if you want to recover them from a Riemannian manifold, well, from a Lorentzian signature manifold, then you have to add explicit torsion in the manifold. You couldn't do that just with the Levi-Civita connection, right? Questions? Okay, so yes. This is boost invariant by construction. No. No, this is independent. Well, I mean, I don't know how you should say it. Why you would want to I'm not sure I got what you're saying. Yes. That's true. Okay. You're saying that mu is changing. But this is also, wouldn't that be true also in Lorentzian signature? So therefore, this is nothing special with Carroll. Well, I'm not sure what I should say about this comment. What I'm saying is that, well, maybe I should state it again. What your comment applies to Lorentz as well. But you change the frame as well. Is the Levi-Civita connection covariantly in which sense? No, wait a minute. No, I think you are mixing things. Here, take Levi-Civita, use Cartan formalism, the metric is remaining unchanged. You change the frame, you change the connection. It's the same. The connection in the frame, I think it's the same, right? Say it again, please. The torsion transforms as a vector under rotations. Now, if you do under boosts, you will transform it. Is this? right? Okay. Okay, that's fine. Then I agree with this comment. No, I agree with this comment, and I agree that the torsion, all the tensors that I have defined here are tensors with respect to rotations. Because when you perform boosts, they will transform within homogeneous species. Okay, if this is a statement, I absolutely agree. Okay, other comments? Okay, so I agree. Now, yeah, I mean, these are, well, this is a parenthesis. It's maybe not necessary to go through it, but nevertheless, it's a parenthesis. There are quantities that appear, and they have a very specific meaning. The only thing that maybe, without taking too much time on this slide, I should quote, is that out of these quantities, you can build another piece of information that is needed in the conformal structures, which is precisely the conformal Weyl connection, which is needed to define a Carrollian covariant, Weyl covariant derivative, because this is what we need on the boundary as well. So this is somehow, the information is contained there, but maybe it is not necessary to discuss. But next step is Carrollian dynamics. And there are two ways to somehow discuss Carrollian equations of motion. These are either you start with, for example, this equation, which is written in the Laurentian signature relativistic dynamics, and then you consider the C goes to limit. But when you do that, of course, you have to assume the behaviors with respect to the powers of C that appear in TAB. This is one option that you can do. The other is to work directly in Carrollian setup. So this is to define momenta, which are conjugate to the geometric variables, no matter how many of these variables you have, and to impose local translation invariance in the Cartan frame or diffeomorphisms in coordinate frame. You do that, you impose these conditions, and you find equations that will actually be substituted to the ones that you had before. Right? These are two possible roads, and maybe I want here to make a few comments because, again, I will not discuss the details of these things, but it's good to have them in mind. First of all, well, this equation, nabla TAB equals to 0, is somehow not the most general that you can write down, right? So even in usual Lorentz relativistic systems, keep in mind, if you have a torsion, for example, this equation is no longer the image of the conservation of the invariance under difference. So this is one thing, and of course, this is even more visible in situations like Carrollian or Galilean. So this is one thing. The other thing that I want also to stress is local boost invariance, which you may have in a theory, Lorentzian signature theory, does not necessarily lead, when C goes to 0, to Carroll or Galilean local boost invariance. Just because to take this limit, you must assume some behaviors regarding to C squared, and the condition that you have Lorentz invariance to start with does not imply anything on the behaviors with respect to the velocity of light. And maybe I should also stress that most of the properties depend on the connection that you are considering. So, for example, there is a statement which tells that in Galilean physics, the momentum equals to the density times the velocity is equivalent to Galilean boost invariance. This again, this is true, but within some conditions and some restrictions on the connection. And I'm here referring, actually, this is nothing very, very deep, although this is old. I'm referring to a seminal paper by Duval and Kunzel, where they exactly discuss the Galilean situation, the Galilean continuous equation of motion, and they quote very precisely, as you may see here, that the equations that they found, these equations that they found, cannot be set in the form of a divergence of an energy momentum tensor equals to 0. So this was so I don't say much with things, so, but when discussing and reading the literature, I should be careful on the statements. So let me give one example. I will not discuss the variation in the momenta. I will just give this example, which is here. So I start with a metric, which is a Lorentzian metric. So it has a finite velocity of light, Levi-Civita connection, and I decompose the energy momentum tensor with respect to a certain congruence. I choose this congruence to be the congruence at rest, because this will be the congruence that will be carrying the field of observers in the Carrollian case. So doing so, the energy momentum tensor is decomposed in longitudinal components, which will be scalars with respect to Carroll, mixed, which will be the vectors, and fully transverse, which will be the stress tensor. This is a symmetric tensor. This can be expanded in powers of C, and demanding that nabla of TAB is 0, which is the relativistic, the Lorentzian equation, you find a sequences of equations at each order of C squared, and they have this form. The P's, all the quantities which are here are the ones that appear in the expansion, right? Now, if you further want to have a conformal situation, well, you can write down these terms in terms of Carrollian covariant derivative. So this is a standard procedure, and these are the typical equations that will appear in the last part of the talk regarding precisely the reconstruction of space-time and the flat holography case. So it is not necessary to discuss details about this equation, but this is the way that appears. And again, coming back maybe to the comment of Yannick, in this case where you have very specific dynamics, well, these bits, the PA which are there, break local Lorentz boosts. But that's the way that appear from the limit. If you want these local Carroll boosts to be maintained, you have to demand that these vanish. But if you find them in a limit of energy momentum tensor, you don't control them. So you get what you have. Good. Let me go to the last part now, which is the application to flat holography. And maybe I should start making a sort of a discussion between reminding what flat versus anti-de Sitter is. So the framework for anti-de Sitter is Einstein spacetimes. These are the spacetimes with negative, in this case, negative cosmological constant. And for those spacetimes, Einstein spacetime, which solve these Einstein's equation, generically there is a finite solution space, and there is generically not gravitational radiation. I say generically because this statement depends, of course, on the conditions that you put on the boundary. And under normal conditions, the ones that are used in ADS-CFT, there is no gravitational radiation, and the solution space is finite. Now, what is anti-de Sitter CFT? Now, this is an incarnation of these ideas of 't Hooft and Susskind, actually, regarding the number of degrees of freedom of a gravitational field. So this is really a statement about a very specific theory, which is gravitation, and the way that it behaves. Now, in the modern language, well, there are two main features. First of all, there are fundamental theories. There is a fundamental theory, which is type 2B string on a specific space, so it's ADS5 cross S5. And there is a gauge field, which is n equals 4 superior Mills on Minkowski spacetime. These are two specific theories, and these theories have each of them a coupling constant that is describing the dynamics of the system. Now, this duality that is set between these two theories is said to be holographic in this framework of anti-de Sitter CFT. And this, again, has a very specific meaning. I should say, summarizing, it carries two bits of information. The first is that the dual field theory, so this n equals 4 super Young-Mills, is defined on a codimensional one time-like hypersurface. So this is one bit of information, and this is the conformal boundary, can be thought as a conformal boundary of ADS5 in the compactified type 2B string theory. But this is not the only reason why this is called holographic, right? There is another reason, which is the role played by vacuum expectation values versus sources. And in this approach, you have, in a sense, two. From the point of view of the boundary, from the point of view of the field theory, these two are conjugate variables. From the point of view of the bulk, these are the two layers of information that you need towards the boundary. So you need the leading and the subleading term. And with these two, from the point of view now of classical general relativity, these are the two pieces of information that you would need to reconstruct the Einstein spacetime. You need the first and second fundamental forms of the conformal boundary, which are physically interpreted as the metric and the energy momentum tensor of the boundary, which are the two dual variables as Vevin sources. And of course, in this game, the boundary energy momentum tensor plays a central role. Now, there is nothing like that actually if you go back to flat spacetimes. There is nothing. There are things, but not exactly this way. First of all, Ricci-flat spacetime have an infinite dimensional solution space. And they do have also generically gravitational radiation. In order to avoid gravitational radiation, you have to take very restricted framework. The conformal boundary, as we have already said, is null rather than time-like. And there is no clear concept of boundary energy momentum tensor. But the last statement, you disagree on the last? You don't disagree on the first? On the first?
Okay.
Yeah. No, I agree. Three are peculiar. Okay, that's true. Three are peculiar. The gravitational radiation is not present the way that we have usually. That's true. No, this is in fore, probably also higher, but then even in higher there are other things that you can say. This is in fore. Okay, good. Agreed. Other comments? You will show what? Oh. Okay, I will also say a few things. But here, what I'm saying is that at first glance, when you study, Ricci-flat spacetimes, and well, there are no clear concepts that come immediately in the mind. This is what I wanted specifically to stress. Whereas in the case of anti-de Sitter, the energy momentum tensor appears very naturally. But of course, we are all trying to find something that looks like that would be a good energy momentum tensor that would play that role. I absolutely agree. Yes.
For the Carrollian momentum, can be repackaged in
No, that's true. But let me maybe this comment is a little bit provocative, and I'm happy that it worked. No, it won't contradict the comment, but simply what I'm saying is that, there is what I will advocate is that, there is room to dig and try to understand. Otherwise, it wouldn't be discussed, absolutely. Other comments? So, now, this is so far a sort of resume. Now, if we really want to follow this ADS-CFT paradigm, which may not be the case, actually, as we all know, well, I mean, I don't know how to say it in English, but in French there is a saying comparaison n'est pas raison. Now, right? So maybe doing that is not a good idea. But anyway, if we stick on this idea, then we would expect, wait a minute. Okay. We would expect that a dual CFT3, living on the conformal Carrollian boundary, this would be a sort of simple expectation. Well, the theory that is thus defined should be invariant under the conformal Carroll group of the boundary, which turns out to be identified with the BMS group in the bulk. And as you see, I have switched to fore to avoid any further provocation. and possibly this theory and this duality should be multi-sectors, because you have the scattering degrees of freedom, you have bound states, and you have also the deep degrees of freedom in the sense that I mentioned that you need an infinite dimensional of different dimensional pieces of information to reconstruct the Ricci-flat spacetimes, and this is because at any time, the deeper you want to go inside the bulk, the more information you need to specify. This is not something that happens in anti-de Sitter. Yes? Oh, yes. No, no. Okay. This is wishful thinking. No, I have not. This is not because I have a very specific thought on what we should do with the I0 and little I plus and minus. No, this is because, we have been somehow navigating very often in this null boundary, and this is a completely biased approach. I'm agnostic about how this. Actually, I'm agnostic, but this has been discussed. It's antipodal. I will not discuss these issues. The role of I0, the corners, this is certainly an important side, which I will not talk about. Yes, please. Okay, but you still. Where did I talk about flat limit? Yes, no, but that's true. Okay, I will talk about flat limit in the next slide. But I don't disagree with what you're saying. But you have to explore somewhere. Absolutely. So, and I will not discuss topology. So I already answered this part of the question. That's true. But you can still try to figure out where the degrees of freedom of Ricci-flat come when you start from a DS. Now, how they're packaged to provide a certain topology, this is yet another issue that is explored. Thank you. So, as I said, this is a sort of wishful thinking. Again, I insist. This is because we are biased. We know a DSCFT. Well, we know some things of a DSCFT. And again, but I insist, the theory that you may find in the end of the duality may not be local, because you have infinite number of degrees of freedom. You may end up with a non-local theory. You may end up with a non-unitary theory. After all, there is radiation that comes to the boundary. And you may even find a duality which is not even holographic, right? Not holographic because, not any duality should be real. I mean, you can deal things which have codimension 1. That's absolutely true. Now, whether it's holography, if you have infinite number of data that you put, it's not clear to me that you say that you have one information left. That's... No, but if you... No, I'll tell you. What I'm saying, maybe this is an important point. What I'm saying is the following. In a DSCFT, you have two pieces of information close to the boundary that allows to reconstruct the whole bulk, which is leading and subleading. Now, if you still on the boundary project everything that you need, but you have an infinite number of degrees of freedom because you have at every order that you have entered, you need a further piece of degrees of freedom, then, well, it is not clear to me, but this is maybe semantic, whether you should really call that holography. That's what I'm saying. But it's not just because of the infinite number of degrees of freedom that you may need. That's all I'm saying. Yes. That's true.
What I would say is that we will have non-locality and we will have to go
No, right.
Able to
Okay, this is open. I agree, but this is open. This, after all, this is not meant to be stated as a theorem. There are just questions that you may ask to start with, right? Now, what is true is that there has been a sort of different path, which was thoroughly discussed last week, which is the flat fore CFT2 celestial approach. So this is different. First of all, in this case, you have, I mean, this CFT2 is defined on the celestial sphere. Well, in quotation mark, I would say that this is a spatial section of the Carrollian boundary because actually this relation is non-local, right? It's rather projective or non-local, again, use of the full Carrollian boundary, which makes it S2. In this framework, there is a two-dimensional energy momentum tensor, which is built out of a non-local construction of the news. So the formula is more complicated. I make it simply here sketchy, right? The news, so the news which come from the bulk, which carry the information about gravitational radiation, this is what ultimately will describe this energy momentum tensor. Well, this theory is still rather mysterious. And what I want to stress here is this duality is mostly a recasting of scattering properties. Scattering amplitudes, on the one hand, in the bulk, mapped onto correlation functions of this theory on the celestial sphere, right? I insist on that, and this is also in line with soft theorems, but there is, for the moment, no fundamental theory behind, neither on the boundary nor even in the bulk. There is nothing like we said previously in the anti-de Sitter CFT. You don't have two theories with coupling constants related in a certain way, and from which you compute something, and in particular related, for example, through a weak, strong coupling relationship that we had in the case of ADS CFT. I should even add that this is not even bound to gravity, because the scattering can be discussed in the soft theorems for LCT1 particles, as they are discussed for LCT2 particles. So would you then conclude that, for example, electromagnetism has a holographic dual? No. So this is to say that this is somehow related to a specific sector. And the rest is yet to be discovered and understood. Now, yes. Yes, but you can still have the mapping with the electron for spin 1 particles. You can still recover. No, not. You introduced nevertheless the ADS, right? And for the theory, for the fundamental theory, you have a theory of gravity. Now, variations exist. I don't object. But what I'm saying is that these are bits of information that, in my opinion, point towards the fact that you need to go beyond. Now, we can, yes. Yeah, no, maybe. Yes. Okay, so there is, as I said, there is an evolution, which I believe is a first step to reconsider or repackage or rediscuss this celestial approach in a Carrollian holography approach. This is a way of recasting the things that are in 2 dimensions in 2 + 1, where 1 is the Carrollian direction. But this probably more is needed in order to capture the other sectors. Yes. Yeah, I mean, this was my comment, is that this matrix is holographic. And well, again, I don't have in mind, I agree, but I don't have in mind what a true definition could be. So I want to leave this a little bit of room for, alternative definitions. But this is what basically, yes, you can put this way. This is an S-matrix theory. This is fine. I mean, I'm not criticizing. I'm saying that this probably provides a side of the would-be holographic relationship, all right? So, yeah, this is, I said celestial approach actually here to avoid the word holography. But even to be also a little bit on the middle, even Carrollian for the moment shouldn't really be called holography. So exactly. So this is, as I said, this is, I think, a proper way to restate things, but maybe that or anyway, this all points towards somehow precisely what are the other pieces of information, and there is an alternative question, of course, which probably is very hard to answer, is that what can we learn from a DSCFT in the limit lambda equals to 0, so in the limit k equals to 0, so when the velocity of light on the boundary goes to 0. So of course, I have no answer to this question, but in the remaining time, I just want to make a first step, which is what can we learn just from ADS, not from a DSCFT, but from ADS when lambda goes to 0. And this comes back to the questions that you had asked previously. So the answer to this question is the following, is that, by choosing an appropriate gauge and expanding the anti-de Sitter boundary energy momentum tensor in Laurent series with respect to the cosmological constant, and of course, using the tools of Carrollian geometry, one can somehow have a bit of information about what is going on. And the punchline is that, first of all, we can recover the flat data and basic features that I have presented previously for Ricci-flat spacetimes. We recover the flux balance equations that appear in Carrollian dynamics. And the energy momentum tensor actually gets back into the frame beyond the celestial energy momentum tensor. So these are the things that I want to discuss. It won't make me too long, but let's go through the basic steps and try to summarize what comes out. So first of all, if you want to make the IDS to flat, you should choose a gauge that you can use both in ADS and flat. So Pfefferman-Graham, which is very nice in some aspects of anti-de Sitter CFT correspondence, cannot be used. We have been using here the Newman-Unti, actually, and in a slightly modified version, or relaxed version, I should say, which is the covariant Newman-Unti. Newman-Unti is very similar to Bondi. There is a time difference. R is affine in the Newman-Unti, and it is not affine in the Bondi. But being affine makes also life simpler to describe things eventually in Penrose, Newman-Penrose formalism, because you can parallelly transport the frames. This is the point. Now, this is the expression for the Newman-Unti gauge. And, well, there is partial R, del R is null, it's geodesic, and the shear of this object is the CAG, the famous shear that what is called the Bondi shear. Now, the reason why we moved from this gauge to a covariant Newman-Unti gauge is because this is not invariant under Carrollian diffeos, and these are diffeos that you want to make, change time in time and space. So a simple way to undo this caveat and also to introduce Weyl covariance is to trade the du, which is this form, into a more general u. This u is a congruence. This is u is a retarded time. This is a congruence, and this congruence is just more generally a linear combination of time and the angles. Xi are the angles. Right, and this is what ultimately will give the what we have called previously the clock form of the boundary Carrollian geometry, right? So once you do that, I will be very sketchy, right? So try to pick up the main message somehow. Well, you write what you think being the most general expression for the bulk metric. So this should be solving Einstein's equations with the cosmological constant. And for example, here I have assumed that there are no logs. We could have included logs. I mean, this is very specific. So you consider this. This is just an expansion which has just the property that it is while covariant, and from the boundary perspective, it's also invariant under difference, right? So this is the added value with respect to normal Newman-Unti. Now, in this expression, actually, the boundary metric is just expressed here in some Cartan frame, right? And the time direction will ultimately give the clock form in the limit when k goes to 0. So this is the structure, and the other pieces of information are functions of the angles and of the retarded time, and you have now to insert this in Einstein's equation and solve. That's all you can do. Now, doing so, you go step by step at every order, right? So for example, the first order, which is non-trivial, is order R, and this is what tells you that this shear is actually completely determined by another shear. So this is the shear of the partial R, and this is the shear of the congruence U on the boundary. Einstein's equation tells that this should be equal up to constants, and one of these constants is k squared. So this is one piece of information that you need. Then you go at order 1, and at order 1, what you observe is that the Schouten tensor enters in the game. So at order 1, in the bulk metric, you have the Schouten tensor entering exactly as it is in the case of the Pfefferman-Graham expansion. The Schouten tensor of the boundary metric, right? The boundary metric equipped, the boundary is equipped with a natural Leibniz-Vita connection. Here we are doing anti-de Sitter. Now, at next order, this is a 1 over R order. Then you have new functions which appear. These are epsilon, QA, and TAB. 1 plus 2 plus 2. This is 5 more. Now, and they appear in a very simple expression, which is the one which is here. Now, in this expression, not only appear epsilon, q, and tau, which are functions, unknown functions to be determined, but at the same time appears the cotton tensor of the boundary. Again, you remember you have a boundary, there is a metric equipped with the Leibniz-Vita connection, and there is a cotton tensor. This cotton tensor appears there explicitly. And this is now the two somehow different features with respect to Pfefferman-Graham. In Pfefferman-Graham, the energy momentum tensor appears as a whole thing at a certain level of the expansion. The cotton does not appear at all. Here, the cotton appears explicitly, and the energy momentum tensor appears, but split in longitudinal, which is epsilon, mixed, which is q, and transverse, which is tau. This is what you call, actually, this is how you reconstruct the energy momentum tensor. And imposing Einstein's equation just tells you that this energy momentum tensor should be conserved. Now, when you go further in orders, well, you have more terms, of course, but all these are expressed in terms of the previous. So you don't have any new bit of information. So this is expected. This is performed in this Newman-Unti gauge or covariant Newman-Unti gauge. Finally, you have a boundary metric, which is free. I'm not doing holography, so I haven't fixed it and locked it to be the standard way. I just leave it free. And you have an energy momentum tensor, which is also free, but should, of course, obey this equation, which is there. So this is all we have. And now comes the question to take this set of information and consider the limit when k goes to 0 and see what we can extract, at least at this very modest level of anti-de Sitter. So again, this is, I have not changed anything. This is the same expression that I had previously. The k's are explicit, and I want to consider the limit of this expression together with the limit of the Onsen-Lenz conditions, which were, you remember, the relationship between the two shears that was also a result of Einstein's equations, and the conservation of the energy momentum tensor, which was also mirroring Einstein's equations. So the first orders are very simple. Now, if you work until this point, All this, the limit is very simple and very straightforward, right? For example, the metric, when k goes to 0, it just selects the spatial part, the transverse part. It becomes Carrollian because you have an explicit k square in the time direction. So this is fine. The congruence U, well, it provides the Carrollian-Ehresmann connection. This is, again, fine. You again find very easily what happens. And of course, from the A, which is there, you recover the Carrollian-Weyl connection that we'll be using later on to describe the Carroll covariant derivatives, Weyl-Carroll covariant derivatives. Till there, somehow, it's very linear. Now, when you get now to the next order, then surprises appear. The next order is order R. And in order R, this is the equations that you had. Now, when you send k to 0, you see that immediately you find two results. The first is that this shear, which was the shear of the congruence, a boundary shear, a purely geometrical quantity, should vanish. So this selects a specific type of Carrollian manifold as null boundary. Like this is a very specific one, it's a specific, it's not a generic one. The second is that CAB is completely free because now it is not bound to be equal to something else. This is the radiation, which is free. This is what you find when you perform this analysis. And now you have to go further. Check what happens in the other orbits. Now, the rule is, of course, very simple. You need the line element to be finite. So you want any time that you have a divergence, you must kill it. And at the same time, you also have to check what the equations. Remember, for the moment, the only equations we have are divergence of t equals 0. And so at order 1, things go smoothly. You trade the sigma for this quantity using Einstein's equations before taking the limit. You take the limit and you find precisely what is expected to be found if you had started from Ricci-flat Einstein's equations. Now, what should we do? Now, what should be done next? Remember, next is 1 over r. 1 over r is where the energy momentum tensor appears. Now, there will be things that will happen and will be new. So the point is that we should actually trade, remember, epsilon, q, and tau. These are pieces of the anti-de Sitter energy momentum tensor. And as I said in one part of the talk, when you have an energy momentum tensor, you shouldn't have a prejudice about the way that it behaves with k, so with the velocity of light. So the best way to do is to Laurent expand this information. So this is the boundary anti-de Sitter energy momentum tensor, and you expand in all possible powers of k. And you insert it back in the line element, right? This is the first thing that you do, as well as in the equations. And then what you do is you consider these equations, which were the anti-de Sitter equations, so the divergence t equals 0. This is one thing that you should consider. And you should also consider the bulk line element and require that this is finite. So this is the principle, right? You insert this Laurent expansion of the energy momentum tensor into the equations and the Einstein, in the equations and in the metric, and you require that everything be finite. And then you follow what you learn. So that's what happens. So in summary, what will happen is that the Chthonian are all these data, Chthonian because these are deep. These are the data that you need to go deeper and deeper inside the bulk. So you discover some of those will vanish. So those will be forgotten. Some will be determined by the cotton tensor, which is very interesting because this will make, as we will see, the relationship between the cotton tensor and the radiation. Some of those will remain in the 9 element, fortunately, because these will be the new functions that you have usually in Ricci-flat spacetimes. And some extra equations will appear, and these will be the equations for these new functions. All this comes from the requirement that the line element be finite. Right? So, as I said, here I mentioned that the Carrollian cotton descendants are just the cotton tensor, which is defined in 3 dimensions, here, boundary, and you can have the Carrollian relatives of this object. These are what I call, these are obtained again by expanding, and you can also write down Chern-Simons action or Carrollian Chern-Simons action for those. People who are interested are welcome to discuss it. Here, this is what you find. This is what you find at the first order, at the first non-trivial order, 1 over R. 3 pieces of information remain in the line element. This is what is the energy density. This will be interpreted as what in Bondi language, the angular momentum. And there is a piece which is a stress tensor, right? Now, and the equation, you remember you had an energy conservation, the nabla T equals 0. This will give for you 2 equations, a time equation. Remember we have split in the beginning the dynamics. There is a time equation and the space equation for Carrollian dynamics. This is a typical Carrollian dynamics, but with a right-hand side, which contains the news and the shear. And this is the source due to the gravitational radiation. So this is very important. Now, and I insist that the cotton tensor enters here everywhere. The cotton tensor captures the radiation of the cotton tensor, and in particular, in this language, the Carrollian limit of this tensor capture the radiation, and at the same time, breaks Carroll boosts. So these are broken just because, you know, this is the information that comes from the gravitational radiation. Yes, Kim, please.
This does not mean that you are in the correction, then you can answer really.
Algebra to the Carroll, you mean?
To the Carroll or to the flat?
Yeah.
You can do both. Corrections like you can do infinite-dimensional algebra with new fields in the game. And wondering if one could use this.
Okay, I understand your question. No, we haven't discussed this. We haven't discussed the algebraic, the symmetry acture. There's the symmetry, the emergence of the symmetry in this case. So I understand what you're saying, but from this language, discussing the symmetries would require, you know, to discuss asymptotic killing vectors. And therefore, well, this is something that has been done thoroughly in other frameworks, not in ours. Now, I don't know how this, what I have suggested here, would match with what you have in mind. This I don't know. Other questions? So I think we are done. I mean, this is the principle is the principle is very simple. As I said, you go at this order, you find what is left in your line element, and you use the equations that you had already, the nabla T equals 0, to recover these equations. These are known equations, right? These are the Bondi loss mass equation, and this is the Bondi angular momentum equation. But these are written in a Carrollian form with a source. Notice that there are also equations which are here. These are identities. These are the magnetic dual, and they concern the cotton, and this concerns the magnetic mass. These are purely Carroll. There is no right-hand side, and this is what I would say, Ashtekar would say, or Ashtekar calls that, like, I mean, he refers to this, well, he doesn't refer to these equations, we refer to his statement that nuts are forever, so the behavior of the magnetic side and the electric side are thoroughly different. Right? So this is important, but both appear, and they both are around the cotton tensor. So if you want to go, for example, at order 1 over R square, let me do this one because then you learn something more. You have more pieces that remain. When I say pieces remain, it's simply because, you know, when you write all these things inside the line element, you have bits of positive powers of K and negative powers of K. The positive powers of K are killing their coefficients because K is sent to 0. The negative powers of K impose constraints. And where there is no K, there is a bit of element that remains in the line element. That's how it appears. Now, the important thing that appears at order 1 over R square, and this is generic for any other order, is that you have a constraint that appears because at some point there is a negative K that should have a vanishing coefficient, and this vanishing coefficient is nothing but this sort of equations that are in quotation mark called flux balance. They are rather constraint equations that are mirroring again Einstein's equations from the point of view of scribe minus. They appear as a requirement of finiteness of the line element, and you can go on at every order. At every order, you'll have a new replica and an equation for the previous replica. So you see there is a replication at every order. There is one piece of Thonian data which appears, which is something new, because you are reaching Ricci-flat rather than anti-de Sitter, and this comes with an equation for the previous one that gives now the full set of equations. And this is the typical equation that you obtain can be mapped nicely, for example, in this formalism of Newton-Penrose, and you have a dictionary which is not worth discussing. Let me now give this final summary of what we have been doing, what I have been presenting here somehow. So there are three, I would say here, conclusions. Lambda equals 0 makes sense. Now, of course, the analysis of the topology is missing, and I agree that this is a first step towards making the relationship between anti-de Sitter and flat. Nevertheless, it can be done successfully because we find exactly all the Einstein's equations that you would find usually doing Ricci-flat approach straightforward. Here is a limit of anti-de Sitter rather than straightforward. They are mapping to Carrollian boundary dynamics, and there is an infinite number of data that emerge in the solution space. And the main message, as I said, is that the boundary energy momentum tensor is now back, in the sense that here we have a boundary energy momentum tensor of anti-de Sitter that comes replicated many times, and each replica has a meaning at every order. If you want to enter deeper, you need that. At the same time, the Carrollian cotton tensor appears. Carrollian. We knew that the relativistic was appearing in anti-de Sitter, but this here appears this is a Carrollian version of it. And it has two features, right? It accounts for gravitational losses, because it appears in the equations where the gravity, the waves appear, the radiation appears, and it breaks Carroll boost, which is also yet another somehow way of seeing the presence of this gravitational radiation, at least in the gauge and in the framework that we have chosen. And it also plays a role, but I haven't discussed this role here, in setting the electric-magnetic duality at the level of gravity. Of course, the aim of all that is to go beyond what is nowadays considered as Carrollian holography and really make it Carrollian, I would say Carrollian Thonian, taking into account somehow all the possible sectors. So the shear and the new celestial sector that appears at order R, but we expect that this energy momentum tensor and all the replicas should at the same time that appear at order 1 over R and higher also play a role in this possible description of holography. And let me thank you. It's time to stop. It's even more than time. I apologize for the delay. Thank you very much.